Welcome to the second video dedicated to the analysis of a bimetallic strip. Before starting speaking about new arguments, let me say one thing that I didn't mention properly in the previous video. If you didn't see it, you can check the description to find the link. Now, I said in the first video that the curvature kappa is not dependent on the width of the strip. This is because the two layers are welded together and they share the same width. This means that the width can be taken out from this parenthesis, and this W can be simplified with the W that appears here. Remember that this was the area, and we didn't write W because we set it equal to 1. One thing that Timoshenko did was to rewrite this expression in another form, introducing two new parameters, N and M, that are respectively the ratio of the Young moduli and the two heights. This is because in many applications you are not interested in knowing the absolute values of these quantities, but rather their ratio. And so, if you recall, this was a paper published in 1925, where computers were still ahead to be invented, and so this helped to perform the calculations. If the two layers have the same height, and so m is equal to 1, the curvature is given by this formula. And you can see that the parameter n, that is the ratio of the two Young moduli, is not really influencing this value. Since almost all metals have Young moduli that are of the same order of magnitude, we can predict that the value of the parameter n will not differ very much from 1. And so if we take, for example, the case of n equal to 2, what we are adding is 2.5, that is this value, to 14. And if we take n equal to 1, we are adding 2, and so on. Consider now this exercise, but please, since I made up many of these data, please focus more on the procedure rather than on the result that we will obtain. So we have to determine the geometry, namely A1 and A2, of a simply supported bimetallic strip made of steel and copper. We know that for a delta temperature of 100 Kelvin degrees, the vertical displacement of the midpoint must be 2.5 micrometers. We also know the total length of the strip, that is 1 centimeter. Now, these data that are present here were arbitrarily chosen by me. These instead are actual physical values. Point number 1. Since we know the displacement delta and also the length of the beam, we can compute the corresponding curvature kappa. If you choose a section on a generic beam, you should know that the radius of curvature is defined as the radius of the imaginary circle that is tangent to the beam in that point. Consider now a simply supported beam and its deformed configuration. We can call the midpoint P. If we make the hypothesis that this part will deform as an arc of a circumference, we can say that the two radius of curvature in this point and this one are equal, and we can call them ρ. We have also that this angle is theta and this length is L over 2. We know that the relation between theta and L over 2 is theta times ρ is equal to L over 2. And so if we want to compute this displacement delta, we can write that delta is equal to ρ, that is this, minus ρ cosine theta, that is this one. And so what we can write is delta equal to ρ 1 minus cosine of L over 2ρ, that is this expression. And so you can substitute the value given by the text in this expression and compute the corresponding value of ρ. Please note that this is not an explicit equation, and so you cannot find an expression of the type ρ is equal to something. You have to solve with some solver. But in any case, since this argument is very small, mathematics help us because we know that cosine of x when x is tending to 0 is equal to 1 minus x squared over 2 plus some smaller terms. If we neglect them, we can substitute cosine of L over 2 rho with 1 minus L squared over 8 rho squared. And this, if substituted here, will allow you to solve this expression explicitly. The result you will find using this data is 5 meters. Point number 2. Now that we know the curvature, we can compute the m value using the equation that we derived in the previous video. So, knowing this, we can use this expression to find m. That, recall, is the ratio of the two heights. To solve this equation, we need another data that is n, the ratio of the two young moduli. It was not given at the beginning, so I wrote it here. For steel and copper, the ratio is 1.74 and something. Okay, if you substitute the values inside, you can see that for a given value of curvature, actually it depends also on the total height of the section. So we have two unknowns, m, that is the ratio of the single heights, and h, that is the sum of these heights. What I did here was to plot this expression. So I wrote it in the form like h equal to f of m. And so on the x-axis you have the m coefficient, and on the y-axis you have the total height of the section. And you see that for a fixed value of h, mathematics says two possible values of m exist. But since all this work is based on the hypothesis that the strip was slender, we cannot definitely choose a value of the total height greater than 1 millimeter, because recall that the total length of the strip was 10 millimeters. In other cases, the hypothesis of slender body is not so meaningful. As an example, I've chosen m equal to 0.05, so we are like here, and this leads to a total height that is around 1 millimeter, A1 and A2 that are fairly different. One is 50 micrometers and the other one is 1.0 millimeters. Even if this is a fictional example, I can tell you that laser metal deposition and other additive manufacturing techniques can allow you to have such a small layer of steel. We are now arrived to the third and last point of this exercise. We have defined the geometry of the beam, and therefore we can compute the trend of stresses in a generic cross-section. In general, if delta T is greater than 0, the maximum tensile stress will be generated on the bearing surface BS. If layer 1 is considered, one can write, and here we are now applying the superposition principle. So we will say that the sigma on the bearing surface, considering just layer 1, will be a sum of an axial stress given by this force P plus a bending stress given by the moment M1. Now you can watch the first video to see from where these expressions are coming. This is the axial stress and is a force over an area. We set the width equal to 1. This instead is giving you the stress on a beam that is subjected to a bending moment. Recall that P has this expression for a bimetallic strip. This was coming from the equilibrium equation, and so if we substitute the values inside those expressions, here we are computing axial stress and here bending, we can find these numerical values. But more importantly is the trend. The axial stress is constant through the section, so this is the sigma axial. Instead, the bending stress has a butterfly distribution, and here is positive. So what we have to do to plot the final stress in layer 1 is to sum a constant term plus a linear term. This is plus and this is minus. So this is what happens. The final shape of the stress would be the black one. And of course, the shape depends on the absolute values that these two stresses have. We are now arrived to the last part of the video, I computed in exactly the same manner the stresses on the second layer using the value of P that is equal for both the layers, and this time using the lumped moment M2 instead of M1. And so these are the results that you will obtain using the same formulas. But now what you can see is that both the axial stress and the bending stress will be compressive. So this was a positive, this was positive here and negative here, this is negative, and this is negative here and positive here. So on the bearing surface you will actually have a really huge difference in stresses, because you are passing suddenly from a negative value to a positive one, and also for the bending you are passing from a negative to a positive. And since we are considering the elastic case, you know that between stresses and strains a linear relation exists, so this will be the trend also of the strains. So with this consideration, we have concluded the series of videos dedicated to the analysis of a bimetallic strip. I hope you found them interesting, and see you on the next one.